Okay, today we are looking at chapter 7 or lecture 7, which is design and implementation in software engineering. So this lecture is actually broken into two. We have lecture 1 and lecture 2, and we are saying that the software engineering design and implementation is actually intertwined, or they go together or interleaved. That's why we put it together, because when you design the software, and then the implementation thereof happens. So under this, we look at these particular topics. We have object-oriented design using the UML. We have design patterns. We have implementation issues. We have open source development, and then we have so basically these are the topics. Now we look at design and implementation itself. So we are saying that it's at a stage where executable files are developed in the software development process. So when customer requirements are solicited or elicited from the client, the design actually happens, which identify the components and the relationship in it. So after that, the design itself is implemented, and then the executable software is generated. The design and implementation stage, we also look at whether you buy the software or you build it yourself. So we have what you call commercial off-the-shelf systems, which is normally systems that has already been built, and then you adapt and reconfigure to suit your needs. So that means that with that one, when you buy the software, you also go back to your requirements and look at your design once more and be able to configure it to meet that needs. So the software also look at the object-oriented design process. So with the object-oriented design process, we see the structured object-oriented process, where you actually look at all the objects that are relevant to the system that you are designing. It is not cost effective when you are designing a small system, but actually when you are designing a big system, it's very important to look at it really. With that, you can also look at the data flow models. We look at state machine models. We look at behavioral models and many other models that are very important to the process. So for small systems, it's really not important. It's not cost effective for using this. Yes. So the next process, we look at the process stages at which the object-oriented design goes through. Since there are a variety of different object-oriented designs process that depends on the organization's choice. So based on what the organization chooses, you may have a different design for it. So in this stage, we have 5 different processes in doing that process. So or in identifying the object-oriented design process. So one, we have the define the context and use of and mode of use of the system, and we have design the system architecture. We have the identify the principal system objectives, specify object interface, and specify object interfaces. So these are basically the 5 basic processes that you need to go through when you are actually going through the object-oriented design process. So we will illustrate this in the next sheet, where we actually look into the weather station software. So what we will do here is that we look at the context and then the interaction models, and then we will relate this to a weather applications or a weather station operations, and see how this all comes into reality by in the design and the implementation model. First, the understanding the relationship between the software and its environment. So what it means is that when you are designing and implementing it, you need to understand what the software and then its environment is, and also in that case, what is that you provide the required system functionalities and also the structure the system of the system to communicate with its environment. So it means that you need to know what are the functionalities of the system, and then what are the structures of the system, and then it helps you be able to know how it communicates with its environment. The environment can be other systems or whatever that is in the software environment. So it also helps you to identify the boundary of the of the system that is being designed. So in this case, when we look at context model, we talk about the features of the systems that is being designed, and when we talk about interaction, we are saying that is the communication between a system and its environment. So here we look at two things here, context and the interaction here. So we have two basic diagrams here and then 2 points here. So what we are saying is that the context system or the system context model is a structure model that demonstrates the other systems in the environment. And then see, so that's the first one, the system context model. Is actually showing other systems in the environment and the role they play. So here you see the source system, the role it plays, and then the target system, the role it plays. And then when you look at the interactive model, we also look at the dynamic model that shows how the system interacts with its environment and as it's being used. So here we talk about the role. The first context model, we talk about the roles that they play, but here we are looking at in the interaction of the two systems, how it's being used. Let's say there's a transfer of actual information from one system to another. That's why we see that an interaction between the two systems is happening. And here is a context model of a weather station where we have the control systems, weather information systems. We look at weather station and then the satellite. What it means is that the weather station is actually the hardware environment that is collecting all the information from the weather and the instruments, and then this information is needed by the weather information system. So what it means is that the weather information system will signal the satellite that maybe information is needed within every hour. Then this particular weather station will have to organize the data and then summarize everything and forward it back through the control system onto the system that requested the information to process, which is the weather information system. So here is a use case diagram of how this can also be represented, a use case diagram. So what it means that we have the control systems, which restart, shut down, reconfigure, and then power, save mode, and then remote control. So that is all the system that is doing these functions in the system. And then we have the weather information system also actually looking at the weather report and then the weather status, all those things. So it's actually doing the processing at the other side. So basically here it explains exactly how the information is where in the use case diagram, the actors, which are the weather information system and the weather station. And this is how it describes the weather station sends a summary of the weather data that has been collected from the instrument to the weather information system. The data sent are the maximum, the minimum, and the average ground and temperature, air temperature. The maximum, minimum, and the average air temperature, the maximum, minimum, and average wind speed, the total rainfall, and the wind direction are samples of 5-minute intervals. So these ones are done maybe 5-minute interval or sent to the workstation. So basically this is how the use case is explaining to us. And then when the data is so when we look at the weather information system, establish a satellite link with the workstation, and then the data is sent to a request for the information. So in the response, the weather station will just summarize the weather information and send it to the weather information system for further processing. So here we also look at architectural designs. So the architectural designs are actually the interactions that happens between the system and its environment that leads the design of the system architecture. So what it means is that we have the system and its environment, but what interactions happens between them. So these are various architectural designs that you do based on the customer's needs, and you need to be able to understand this before you do that. So the system architecture also consists of different components, okay, and these components are organized in an architectural pattern such as client server or layer models. So here, and the images that you see here, we have the client server as the first one, we have the layered as the second one. So depending on the situation or the request and the requirement of the client and the design that has been given, you can actually use this pattern, architectural pattern, to implement your actual design. So here we look at data collection system. So when you are actually the architecture for data collection system, so you see the weather station actually gather the weather data, and then it transmits that data to the receiver. So it transmits and then it goes to the data system. So the weather information, weather station is actually picking the data and weather data and transmitting it to the weather information system when the request is sent. So the request is coming in form of receiver, and then the transmission is also sent to the weather information system. So we also look at object classification, class identification. So in object class identification, identifying object classes is often difficult part of the object-oriented design, because it is difficult because it's now that you are going to look at the system, the requirement, everything, and be able to say, okay, this and this are the object that is needed in the system, and it's quite difficult. And there is no magic formula for object identification. It relies on the skills and the experience of the person, or the domain expertise of the system in a designer, to be able to extract it. So if somebody who have done this for quite a number of time will be able to design it easily, but if you are not so experienced in it, find it difficult. And that leads to the 10 point. So it means that the object identification is an iterative process. If there's no, it's not likely that you'll be able to get a thing in the first time. So what it means is that if you do it the first time and you go and iterate through again, you'll be able to see that, okay, these are the gaps that are in it, and you'll be able to fill it as you go forward. So this is a diagram that helps us to be able to understand how to the approaches of the identification. So first, what you do is you use a grammatical approach where you use natural language to describe the system and how and the methods therein. So this is maybe we have a student that we are going to store information on. In the student, what are the things that we want to be able to save the student data? We need to update the students information. We also need to be able to update student school fees and all those things. These are the things that help you be able to identify how those things are. So based on the identification of the tangible things in the application domain, so if you get in the application domain, you're able to identify the tangible things in it, then that will just lead you to identify either use the behavioral approach or the scenario-based approach. So with the behavioral approach, that's where you identify the object based on what participates in what behavior. So it's the object participates in this or it does this, then you use it to do. But the other scenario project, you identify the object, the attributes and methods in each scenario. So that will help you to be able to identify the objects that are in a particular system that needs to be designed. So we are looking at our weather station example again. In this package, we are looking at only the weather station, which is where we have the hardware instrument that is being used to collect information. So we say it collects data, and then it's perform the data processing, and then onward transmission of that data to the so upon issuing. So first we look at data is collected periodically, and then upon issuing command, the weather data is transmitted. The weather station processes and summarizes the data collected. The summarized data is transmitted to the mapped computer when a request is received. So that means that it's the instruments in here is collecting all the information that is in there and then transmitting it to the weather information system. So that's the function of the weather station, and that's how it works. So exactly what we've explained. And then now we look at weather station object classification. So now that we have been able to explain exactly what the weather station is doing, now we are saying we're going to identify the class object classes in that particular system. So what we are saying is that there we have the ground thermometer, we have the anemometer, and then we have the barometer. So and then we have the weather station itself, and then weather data. So these ones, it's helping you to. So the first one, which are the devices that we talk about in there, are the domain object or the hardware objects that relate to the instrument in the system. So it means that the hardware is one of the objects that can be identified, and the weather station itself is the basic interface of the weather station to its environment. So this is the weather station itself. The devices are there, the weather station itself, and then the data is the encapsulated summarized data from the instrument. So what it means is that the summary, so the weather station is serving as the basic interface of the weather station to its environment. So all the environment, the devices are there, and then or the weather station is serving as an interface and doing all the collection of those weather information and doing all the summary thereof. And the weather data is the data that is received from the devices and processed. So these are the basic ones that you can objects that we can identify from the weather station example that we had. So in here, what you see is that you see the objects or the class names, which are the weather station, weather data, the ground thermometer, the anemometer, and then the barometer. So and then the second portion that we have there actually look at the data members of the system, or we can say the attributes of that particular systems, and then the methods of which you can call to be able to get that particular information from the system. So these are the interfaces, the methods are the interfaces that you can actually communicate with that object. So we have the design models, which shows how the objects and object classes relationship between and their entities. So what it means is that it shows the object and then the object classes and then the relationship between the entities. And then we have static model and the dynamic model. The static model look at the static structure of the system in terms of objects and relationship, and then the dynamic also look at the dynamic interaction between the objects. So here we look at some examples of it. So we say that subsystem models, that it shows the logical grouping of the object into coherent subsystems. So we look at the objects that are similar in nature, and then we group them into it. Therefore, this model will group them into a coherent subsystems. And then we look at sequence models that show the sequence of the interactions between the objects. And then we look at state machine model that shows the individual object and the changes or the event changes that comes in, or the state, the change of state of our particular object. So if the object changes state, then this model will be able to handle it, that particular design very well. So and then we have other models also include use case models, aggregation models, and then generalization models. So here in this systems we are looking at the subsystem models. So here you look at the weather station subsystem. So what we see is that the instruments are in one area, which is one system. So we mean that because they are similar, they are all instruments, as group them as one particular subsystem, and we are looking at interface as one subsystem where we have the command controls and then the weather station, and then we have the data collection models where we have the weather data and then the instrument status in there. So this is how the system models is used to actually group the subsystems in a particular application or a particular model that is being designed. So we have the sequence diagram. I think we have explained this earlier, but we need to just tap it one more time. So the sequence model shows a sequence of object interactions that takes place. So how the object interacts with each other. So we see the objects are arranged in a horizontal. So this is how it's being done. The objects are arranged in a horizontal across the top, and then time is illustrated vertically too. So models are read top to bottom. Interactions are represented by labeled arrows, different style, so different styles of arrows represent different type of interaction. So what we will see that in the next slide, where we look at this diagram and how it has been done. And then a thin rectangle in an object's life represent the time when the object is controlling objects in the system. So here we have a sample sequence diagrams that shows the actors. So we have a system, can be a system or a person. We have the command controls, and then the weather station, and then the weather data. These are the objects that we have identified in a system, and we have the request being made to the command control, and it acknowledges this particular it acknowledges the request. And then you see what it means is that the time that it takes. So here is the interactions that is happening between the two objects. And then so same way the weather station, also the command control send a report to the weather station, and then the weather station will then summarize the request data, and then it therefore also relates that information back to the weather station. The weather station will send it back also to the command control, and the command control will relate it into the information system. So this is how this sequence diagram presents the information for you to see. But what we say is that sequence diagrams are implemented it actually implements much details into the functionalities and how they really operate. And so in small systems that you don't need much details, those sequence state diagrams are not implemented. Sequence diagrams are not implemented in there. So we have state diagrams shows how objects respond to the different service requests. So state diagrams are useful to note objects runtime behavior. So we look at examples of this where at a certain particular time the object itself is there, but in runtime it changes behavior, and thus behavior communicate with other objects to send information. So that behavior is what we look at with the state diagram. You don't need a state diagrams for all the system objects in the system. So what it means that state diagrams are important not for all the objects in the systems. Many objects in a system are relatively simple, and a state model add unnecessary details to that particular design. So here is an example of the weather station state diagrams where we start and shut down. So when we shut down, we do the configuration. So the system restart goes in here. The moment the restart system shut down and restart, it goes in here. As it's running, the controls are in there. So the request and then the response for the weather controls are in there. So what it means is that we send a test of control or to the workstation, and then weather station, and then the data transmission also happen. It summarizes everything. So what happens that it summarizes everything. The data comes back to the transmitting. So what happens in each state is that the system starts and shuts down. When a restart is happening, the system will start running. It will go collecting data, and then the data will be summarized. When the data is summarized, it's transmitted and it's tested, and then it's used. So when the data is also transmitted, it comes back to the main system again, it's also come back, and then they shut down. The system will then shut down. So all these are the details part of the state diagram. So these details is not needed in all the object models that you identify in the system. So we also look at interface. So interface is actually what actually is between the, it's almost always used to hide the functionalities in the system. So object interface are specified in order to provide definition to the method. So what it means that there's a method, and that method has to be executed. So we find an interface that will be able to interact with that particular method. It hides the actual implementation of the objects from the outside world. And then so we will look at it from this perspective. Like, let's say you have a television and you want to turn it on and off, the volume up and down. So what it means that an interface is provided on the television to click on it. You don't actually see the functions that performs the turn off and turn on and then volume up and down, but you have interface to click on it to perform that particular functions. That's what we talk about. So those are the interfaces between you and then the television that you are operating. Objects have several interfaces, which are viewpoints on the method provided. So this is actually what we mean by interface specification. And then this is like a class with a method inside, that this method serves as the interfaces of which you can execute and receive response, or receive response and use it in other particular applications. So what it means that when you say start, there's a method here to start the workstation. When you say stop, there's a method to stop. And when you say test, there's a method to test and then get a report back, calibrate that devices that are in there. All those things are interfaces that can be provided. So when you go to the device itself that you are using, the weather station device that you are using, where the instruments are there are knobs and other things that you can use to do. So those are the interfaces that you need to be able to help you out. So basically this is a summary of what we've done so far. We will just rest more and then go back to the lecture 2. Okay, welcome back to the lecture 2 of the design and implementation phase in the software engineering process. Here we look at design patterns. So what we do is that let's look at this particular 5 items, which explains into details what design patterns are. The design pattern describes a proven approach to dealing with a common situation in programming stroke design. So what means that it is a proven approach, means that we have used that approach for some time. It's a proven approach to dealing with common situations in programming stroke design. So what it means then is that these are methods that have been proven and have been used. So the second point says that suggest what to do to obtain an elegant, modifiable, extendable, flexible, and reusable system or component. So what it means is that if you are actually using any of those design patterns, it helps you to be able to do something that is modifiable, that can be extendable, that's flexible, and the code can also be reused in other systems that you design. So the next point we look at, show at design time how to avoid problems that may occur. So actually when you are using the design part, it shows you what problems you are likely to face. So and you can use that to be able to say, okay, then this is how I tackle the problems when I get there. So these are the ways you also go about those ones. And then we have the fourth point, which says it's independent of specific context or language. So what it means that it's independent of the other context that has been defined or any language. So it helps you to visualize all the designs in independent way of all the other contexts and other things that we have looked at. And the last point, a description of the recurrent problems of the core of possible solutions. So it helps you to know problems that are likely to reoccur and how to solve those problems going forward. So what we look at it is that this is pattern element. So the pattern element is this. So if you have any pattern, the first is the identifier. That is the name of that particular pattern that you are using. The consequences are the trade-offs that the results and the trade of applying that particular pattern. So it means that it shows you what you're going to get, and then the sacrifices that you will make, or the issues that will be inherent in there, or the sacrifice that you make towards that choosing that particular model over others. And a description of overall description of the puzzle of the pattern that you are using. Then we have problem description. So that's describe the situation where to use this particular pattern. So all the patterns will have to tell you that, okay, in this situation, this pattern is more suitable than the other. And then the solution description, a template for a design that can be instantiated in different ways. Okay, so basically this is what we look at pattern elements. And then this is just what we just finished describing. And then this is the behavior, the observer pattern. So this pattern, what we are saying that the name is the observer. The description is, under description we have it separates the display of the object state from the object itself. So the object state is that this is time. At this time, this is what happens. Okay, at this time the bell system goes on. So it describes the object state itself from the object itself. So this one, the time system, is separated from the state itself. So as we go on, we will explain much into that. Problem description used when multiple display of a data states are needed. Let's say you have a data of grades, and you say that, okay, so if a student gets 40 is A, 30 is B, 25 is C. So and then there's that data is displayed on a bar chart and a pie chart at the same time. So what it means is that you are displaying the state of that particular data in different objects, and that is when you need the observer pattern to use. And then the consequence of it is optimization to enhance display performance for impractical objects. So here we look at, this is the description that we've already put. So let's look at this scenario. So that's the scenario that I was mentioned earlier, multiple display using observer pattern. So here we have the observer 1, observer 2, and the subject is, let's say, the information of which we are using to present, or the object of which we are using to present the information onto the two different displays. So we are saying the observer 1 is the pie chart and the observer 2 is the pie chart. They are displaying the same information. So as and when the data changes here, these two displays are updated accordingly. So that is when you need. And then we have the UML model of the subject, the observer pattern as we have described. And then we have the design problem. So let's look at design problems here. Okay, so we say to use patterns in your design, you need to recognize that any design problem you are facing may have an associated pattern that can be applied. This therefore means that there are these patterns that are available. So depending on what problem you are facing, you choose the design that is appropriate for it. So if you want to use the observer pattern, what problem will make you use the observer pattern? Here we have tell several objects that the state of some other object have changed. So if you want to, if that is your problem, to tell several objects that the state of another object have changed, then use the observer pattern. So the other one, the facade the pattern is tidy up the interface to a number of related objects that have often been developed incrementally. So that if that is the problem, then use the facade pattern. And then we have the decorator pattern, so which allows for the possibility of extending the functionality of an existing class to run at runtime. So if that is your problem that you need to solve, then you can use the decorator pattern. And then we have iterator pattern, which also the problem in the context at which you can use this particular pattern is provide a standard way of assessing the elements in a collection, irrespective of how the data is implemented. Okay, so basically these are the problems or the design problems that will make you to make the following choices from these ones. And then the implementation issue. So that was one of our main programs that we wanted to look at. Implementation, when you are implementing the system. So focus here is not on the programming. Now programming is done. We are looking at the other ways of actually implementing the implementations that we're going to face going forward. Although there is an obvious importance, but there's an obvious importance on the programming aspect, but on the implementation issues that are often not covered in the programming test. So within the programming test, some of the implementation must not be issued. So in my context, let's say if you are using a programming language to design and you have not actually implemented it anywhere, sometimes your program might be running fine and okay, but when you start implementing it, you see that there's an other difficulty in implementing it than even designing. You don't know the servers, what software requirement on the server that you are going to deploy on, and that is very critical in any of the things that we do. So here we are looking at three things: reuse, configuration management, and target host. So reuse is when you have other components of an existing system that you want to use in a new system. And then we have configuration management, which actually help us to be able to track many different versions of each software component. And we have the host to target development. That means that production software does not usually execute on the same computer as the development environment. So it is very important that sometimes when you are developing softwares and you are implementing them, the production and the development environment does not stay at one place. So it's very important. So here we look at reuse, how to reuse codes. So in the 1960s, when you want to do any software development, you have to start from scratch and program in high-level programming language. But coming to 1990s, we started taking advantage of code reusabilities and then be able to help reduce the program time. Other significant reuse of software was the reuse of functions and objects in programming language libraries. So what it means is that we started using libraries, which is actually another functionalities that we are importing into our program, and that means that it's going to reduce the time and the cost that will be involved in that particular work that you are doing. Cost and schedule pressure means that this approach become increasingly unviable, especially for commercial and internet-based systems. So basically, when you look at reuse, this is exactly what we mean: bringing other codes that has already been designed and tested into your code and making use of them. So the reusable levels, we have the 4 basic reusable levels that we have. Let's start from the bottom where we have the abstract levels. See, at this level, you don't reuse software directly, but use knowledge of successful abstractions in the design of your software. So that means that place you have knowledge already built up. So that one, you are not actually using the components directly into your application, but you are using the knowledge that has been put there to be able to structure and build your software design from there. So we look at the object level. At this level, you directly reuse objects from a library rather than writing the code yourself, and I think this is self-explanatory. Components are collections. So at the component level, they are a collection of objects and object classes that are that you use in application systems. So it means that here you are just using part of some of the code at the object level. You have maybe one object or the code that is from it, but here you are using objects and then the classes of objects that in the application you want to import it directly into your application to use. And then at this level at the system level, at this level you reuse entire application system. So that means that you have an application that is actually reusable in the things that you are doing. We just import the whole system into application and then use it to do whatever you want to do with it. So sometimes there are a lot of costs that is involved in reusing a code. What are these costs? The first is the cost of the time spent in looking for the software to reuse. So that is a cost that you know that you're going to involve some cost in looking for what you want to reuse in your application. We look at here where the cost of integrating reusable software. So when you have also gotten the software, what are the costs that is involved for you to be able to implement that cost in your application that you want to use? And then where applicable, the cost of buying and reusing the code, or buying the code. So what it means that if you got it, you may have to purchase some of the components may have to be purchased. So if you need to purchase that particular software, what are the costs that is involved there? And the cost of adapting and configuring reusable software components. So if you get the software and you have to reconfigure it, that is also another cost that you need to look at. So reusability always does not come free. You might have to pay something in other aspect of it, including looking for the software, looking at integration into the software, either buying the components of that particular reusable code, and also how to configure the software to be able to suit your requirements and your needs. And then we look at configuration management. So is a name that is given to a general process of managing change software system. So in actual sense, it helps us to be able to manage different versions of the software that you design. So looking at much into details, we have configuration management activities. So first, the version management. So this is where support is provided to keep track of the different versions of the software components. So maybe you have different versions of the software. This configuration management helps you to be able to keep track of the different versions of the software. We also have system integration. This is where support is provided to help developers define what version of the components are used to create other versions. So if you have version 1 and it was created, let's say you have version 5 and it's created from version 2, not version 3. All those things are kept there so that the developers understand and be able to use the correct things in building their application. And then the program tracking. That's where support is provided to allow users to report bugs and other problems, to allow for developers to see who is working on these problems and where to fix it. This is very, very important, because if you don't manage the project well, sometimes it's very difficult. You don't know who is doing what, and sometimes either you ignore a problem or the problem is overlooked, or you get two people working on a problem at the same time. So you look at who this one has been assigned to A, he's working on it, B is also working on this, and then it will help you to be able to manage the project very well. Very, very important point in this. And then the host target development. So in the development platform, he has this other software that is installed on Windows and is using let's say Internet Explorer. But when you go to the, let's say, the target environment, you can say, okay, Mozilla is comfortable in there, or is used there, and then maybe use Linux or whatever in there. So at a hardware level, you determine, because on your test environment that you are developing the software, you might not need high specifications in doing anything. But in the production environment, based on the non-functional requirement that has been given, or the system specification that you need for the system to run, or the expected number of people that is going to hit your server, you need a higher version of it. So all those things mean that the host and the target will never be the same. So you need to be able to make sure that your target is able to handle all the requests that is your client is looking for. So the next one, we look at development platform tools. So when you are developing an application, what are the tools that you need? First, an integrated compiler or a syntax-directed editing system that allow you to create, edit, and compile your code. So we will be looking at IDEs and other things. So a language debugging system. So what language are you going to use? So first you get an IDE, you get a language. So graphic tools that helps you to be able to edit your UML and other things. So there are different tools that people use to be able to design your UMLs and other things. And then testing tool that is used to test. Sometimes you need to load testing to see whether the service that has been developed or whatever that has been developed, if you have more clients and other things, will the system be able to handle? So all those tools has to be available for you to be tested. And project support tools that help you to organize the code for different development projects. So here we have an IDE. So you are using your IDEs. Let's say if you are using Java, you can say I'm using Eclipse or I'm using NetBeans. All those things are IDEs. So we say software development tools are often grouped to create an integrated development environment, which is an IDE. And an IDE is a set of tools that support different aspects of software development with some common frameworks and user interface. So sometimes you look at one interface, another, maybe they may look similar depending on the IDE that you are using. Let's say you are looking at different let's say NetBeans and Eclipse. They might see similar menus and other things, but the way they organize other things might be different. So IDEs are created to support development in a specific programming language such as Java. An IDE may be developed especially or may be an instantiation of a general purpose IDE which specify language support tools. So like if you are using VS Code, it's one in many. It's actually one IDE. You can use it to do PHP, you can do it to do Flutter, you can use it to do Python and all of that. So it means that is one IDE that supports a number of languages. So we have component and system deployment factors. So if you are deploying components or you are deploying a system, what are the factors that you need to look at? First, if a component is designed for specific hardware architecture or relies on some other software system, it must obviously be deployed on a platform that provides the required hardware and software. So before you deploy your system, make sure that the hardware and then the hardware and the software that requires for the software to be deployed are in there before you start deploying, unless you create issues for yourself. And then we also have high availability systems may require components to be deployed on more than one platform. So let's say you are deploying an application for a mobile application. Because of the different environment that we have, Android and iOS, and then Windows, you might have to deploy either on iOS and Android, or if you want more of this thing, you can do on Windows as well. So these ones you need to be able to deploy on a cross-platform environment. That's why it's very important you make the right choice as to which of the platforms that you use for your development. If there is a high level communication traffic between components, it usually makes sense to deploy them on the same components or platform that are physically close to each other. So sometimes they have what we call compute, which means that if one component is on one server and the other component is on another server and they are communicating, sometimes you inherit some other cost in addition to your normal cost. But if they are basically on the same server and other things, those costs are not incurred. So the last part that we are looking at in this tutorial is the open source development. So when we say open source development, what does it mean? Open source development is an approach to which software development is so open source development is an approach to software development in which the source code of the software system is published and volunteers are invited to participate in the development process. So it means that the software is first created by one organization or a particular person, and then the person says, okay, volunteers come in, and then all of us develop. So what it means is that you can also take that software and use it in your other projects, and then you can use it for free. Its roots are in the Free Software Foundation, which advocates that source code should not be proprietary, but rather should always be available for users to examine and modify as they wish. So it means that you can take those software, modify it as you wish, and use it to do whatever project that you want to do. Open source software extendable this idea. Open source software extended this idea by using an internet to recruit a much larger population of volunteer developers. Many of them are also users of the code. So sometimes you have volunteers of people working on the system, and they are also system developers. They use the software to also do their other projects. So what we know of is that Linux is one of the open source software that we need. We also, many of us just use it. You develop it for your server and your, let's say, your standalone applications or the user applications that you use. It is free, and then it's widely used system for servers because most of the time it's free and it has all the components in there. And then we have something like other products also, like Java, the Apache Web Server, MySQL, PostgreSQL. All those are also open source applications that you can also adapt and make modification to it as and when you wish. So the next thing that we look at it is that we look at open source business. So what they do is that they use an open source approach to develop. When we say an open source business, it means that they use open source approach to develop those process, and then actually their business model is not relatively on selling a software product, but on selling support to that product. So what it means is that if you are doing open source business, the software is actually created for free, but the support that they are going to give you on it, you pay for it. So in actual sense, they are making money out of the open source project that has been done, and that is one of the ways that is going, because you, that is a developer, will not incur any additional cost in acquiring the software, but in providing software to the client, you make money out of it. So one other important is the open source licensing. It's very important we look at this because if you are taking any open source project, what are the license agreements on it, and how are you going to use it, and then will not get any legal issues out of it. A fundamental principle of open source development is that source code should be freely available. This does not mean that anyone can do as they wish with that code. Okay, legally, a developer of the code, either a company or an individual, still owns the code. They can place restriction on it, on how it is used by legal binding conditions in an open source license. So I think when we read all the other things, we will understand. It means that there are other different version of open source licensing. So depending on what the license is, it might either be freely available, or it may have some level of restriction for the use. Some open source developers believe that if an open source component is used to develop a new system, then the new the system should also be open source, and that is one of the things that we it's a very difficult decision, because somebody has built an system and it says it's based on open source, so it should be open source. And on the other side is because you have also consumed some open source, why don't you make yours open source? So all these things are things that can be discussed. Others are willing to allow their code to be used without this restriction. The developed system may be proprietary or sold as closed source system. So this is very important. This is very important. So here we look at the three types of open source license models that you need to be aware of before using any other open source project. So anytime they provide any open source project, they give you the licenses that comes with it. So we have the GUN, which is the general public license. So that's mostly GPL. So what it means is that this is so-called reciprocal license. That means that all you use open source software that is licensed under the GPL license, then you must make that source code software open source. So it means that if you use any open source software from this model, then your software should also be open source. Secondly, we look at lesser general public license. In this is a variance of the GPL license, where you can write components that link to the open source code without having to publish the source of this component. So what it means is that the open source thing is somewhere, you are just writing a component to link to it and use it to do your own project. So in that case, you don't have to publish that open source code in your application. You just use it somewhere, and then you use that data to do whatever you want to do. And then we have like using let's say OpenStreetMaps is open source, but what it means is that you just link your application to that open source OpenStreetMaps, and then you use it to build your application. You don't actually host that that program in your application. And then we have the Bakery Standard Distribution License. This is a non-reciprocal license, which means that you are not obliged to republish any changes or modification made to the source code. You can include a source code in proprietary systems that are sold. So all these things, you can look for it and use it as and when you want it, but you need to read and see what the legal implication is in using somebody's open source software under any of these license models. So basically, that's what we have established the license management. Establish a system for maintaining information about open source components that are downloadable and used. Beware of the different type of licenses. So this is what is very important. Always need to read this when you are using any open source project. It says beware of different type of licenses and understand how a component is licensed before it's used. And then beware of evolution patterns of components. Educates people about open source, having auditing systems in place, and then participate in open source community. This is exactly what you need to know about open source development. These are the summary of what we've done, and then that ends our section on design and implementation in software engineering. Thank you all for listening.